Hi everyone, and welcome to the first lesson of Unit 5. And Unit 5 is obviously the last unit, and we won't cover it in the same detail that we would have done had we been in class, but I want to expose you to the idea of working with gases in chemistry and the different kind of ways of seeing it from a theoretical standpoint, but also from a quantitative standpoint or from a calculation standpoint, how you handle gases. And so we're going to be doing a lot of the same things. We'll look at stoichiometry with gases. We'll be looking at calculating the number of moles when you have gases and so on. But for the first lesson, we're going to start with the kinetic molecular theory, so understanding why gases behave they do, and then we're going to look at some of the gas laws. All right, well, let's get going. So first of all, as a bit of a background, obviously we've dealt with this idea that there could be different states of matter. And essentially, we've looked at gases, liquids, and solids. Particles that are in a gas are well separated with no regular arrangement. So let's keep that in mind. Liquids are close together, but they also have no particular arrangement. And solids are tightly packed and they're in a regular pattern. Gases tend to vibrate and move freely at high speed, so they're moving around quickly. Liquids vibrate and move about, but they just slide over one another. And solids, even though they appear not to be moving, they vibrate or jiggle, but generally don't move from place to place. And so this is kind of a bit of a summary of them. Here's the idea of what gas molecules would look like. Here's liquid molecules. And I don't know if you can see it, but these solid molecules are basically just moving a little bit, okay? So this is a nice little summary of the states of matter: gases, liquids, and solids. Okay, so that's a bit of a summary. All right, well, what we're going to use to explain gases is something called the kinetic molecular theory. So it's called KMT for short. And KMT is a theory that will explain why gases behave the way they do. And there are 5 parts of this theory. And these 5 parts will explain why the gas laws are what they are. And then we're going to go into these gas laws. But let's go over these 5 theories. So these are what chemists have said must be true of gases. So first of all, number 1, a gas consists of a large number of molecules or atoms, if it was a noble gas, that are traveling in continuous random motion in straight lines. Okay, so I often draw a little diagram here to make you think about it. And so essentially, if you have a container, you can think of it as all these gas particles just moving around, bouncing off the side of the container, but they're moving in random motion and in straight lines. And I've got a little applet that I'm going to keep referring to, and I thought I'd show you right off the bat. So here it is. And so if I wanted to think about gases, I'll put some gases into this container. And let's just say that this is helium. So helium is going around this container. And these particles are moving in constant random motion. They're bouncing into one another and bouncing into the sides of the container, but they're moving in straight lines and in random motion. This is a good picture I want you to have of gas. Okay, so that's kinetic molecular theory, part number 1. Part number 2 says the volume of all the molecules of the gas is negligible compared to the total volume in which the gas is contained. Basically, it doesn't matter whether you're dealing with a big molecule or a tiny particle like the size of an atom. the size of the gas particle does not matter. It's negligible compared to the total volume of the container. So in other words, you know, this says that whether it's like I said, whether it's a big molecule or a small molecule, you don't have to worry about the size of the molecule. Okay. Number 3, it says the average kinetic energy of the molecule does not change with time as long as the temperature remains constant. Energy can be transferred between molecules during a collision, but the collisions are what we call perfectly elastic. Now, this is a really interesting piece of the kinetic molecular theory. And, you know, a student may look at this picture of these gas molecules and see them moving all around. And the argument they could say is, well, eventually, Mr. Webster, those molecules are going to slow down and then come to a stop, and maybe they're all going to fall to the bottom of the container. Well, the kinetic molecular theory says no. As long as the temperature of this container doesn't change, and look at this, I've set it at 27 degrees Celsius or 300 Kelvin. I'll talk about those in a minute. But as long as that temperature remains the same, these particles are going to continue moving forever. They're going to continue transferring energy around, but essentially they will travel forever like this. Okay, so that's what this third one says. The average kinetic energy does not change with time. And I'm going to tell you that doesn't feel good for a lot of you. Some of you will say, well, oh, come on, eventually they're going to slow down and stop. But according to the kinetic molecular theory, they won't. Okay, number 4, there are no attractive or repulsive forces between molecules. In other words, as molecules pass one another, okay, so if these two particles were to zoom by one another, it's not like they would be affected by one another. They wouldn't either be attracted and move closer together or be repelled and move further away. So this is an important concept. Obviously, we know that if you were dealing with something like the Earth and the Moon, there is an attractive force between those. Or if we were dealing with an electron and a proton, there are forces between them. But between gas molecules, there are no attractive or repulsive forces. And finally, the fifth point in this theory is that the average kinetic energy of a molecule is proportional to the temperature. So in other words, if you increase the temperature, you increase the kinetic energy. So the hotter the gas becomes, the faster they move. Okay? So these are the 5 key things that are going to help us to explain why gases behave the way they do. So this is what chemists came up with as the theory behind it. Now I have this other slide in here that says, I just want to talk about a theory versus a law. And basically, we're going to be moving forward in this lesson covering a series of these gas laws that early chemists established based on their observations. So a lot of these laws we're going to look at go back to the 16 and 1700s. You know, the 1600s is when Boyle and Charles and Avogadro were working on these gas laws. They made these laws based on observation. It wasn't until later that we then came up with a theory to help explain them. And so it says any scientific law is a generalization which describes the results of several experiments. A law, however, only describes the results. It does not explain why they have been obtained. A theory is a description which explains the results of the experiment. The KMT, or the kinetic molecular theory of gases, is a theory that offers an explanation at the atomic level for why the gas laws work. Okay, so we've got 2 things going on here. We've got KMT, which is the kinetic molecular theory. That's the theory. And then, as you're going to see in the coming slides, we've got these various laws. We've got Boyle's law, we've got Charles's law, and so on, etc. So we've got the laws that were the result of all these observations that these early scientists made. Okay, here we go. This is a couple of background things. One of the things that we're going to be talking about is pressure, gas pressure. And this is a concept that we haven't talked about yet, so I thought I'd just quickly mention it. Pressure is equal to the force over a specific area. It's force over area, okay? Force over surface area, okay? And we measure force in a unit called newtons, and we measure surface area in meters squared. And so the pressure is often measured in newtons per meter squared, and that's been given an SI unit called the Pascal, PA. And we often use kilopascals, so 1 kPa is equal to 1,000 pascals. So that's going to be a unit that you're going to start hearing, kilopascals. And if you think about it from an atmospheric pressure standpoint, and basically that's the pressure exerted by Earth's atmosphere on us. So as I stand on the surface of the Earth, right at sea level, the pressure that's on me, the pressure, and if you can think about it as the column of air that goes over top, that column of air exerts 101.3 kPa, kilopascals. And we refer to that as 1 atmosphere of pressure. There's a couple of other units I'm gonna throw in here. It's also called 760 millimeters of mercury, or 760 torr. So these are all units of pressure, okay? But essentially, and they're all equivalent units. But what I'll say is that you mainly in this unit will be dealing with these two right here, kilopascals and atmospheres of pressure. Okay, well, here we go, the first law. So basically, the first law is a law that relates the pressure and the volume of a gas. And what the law states, and this was, it's called Boyle's law. It's based on work done by the chemist Boyle. I forget his first name. I think it's Charles Boyle, actually. But Boyle, and at constant temperature, a gas's volume is inversely proportional to its pressure. Now, it's actually a lot easier than that. Basically, what it says is this, is that pressure is inversely proportional to volume. And what that means is as pressure goes up, the volume goes down, or vice versa, as volume goes up, the pressure goes down. They are inversely proportional to one another. Okay, let's take a look at our applet. Here's our applet. And so what Boyle investigated was he put a gas into a container, and he decided, okay, well, I'm going to vary the volume. I want you to keep your eye right here on the pressure, okay? So I am going to hold the temperature constant. So in other words, I'm going to make sure that the temperature doesn't change. But what I'm going to do is I am going to reduce the volume. And so look at this, we're at 10.7 atmospheres of pressure. And if I cut the volume, it increases the pressure. And hopefully you'll see that, well, sure, Mr. Webster, it's going to increase the pressure because now these gas molecules are going to hit the container a lot more often. And so that therefore they increase the pressure on the container. So they've certainly, as I reduced the volume, I increased the pressure. And the same thing, if I reduce the volume, I spread things way out, I reduce the pressure. Okay, so this is the relationship as you increase the pressure, sorry, as you reduce the volume, you increase the pressure, and vice versa. Okay, so that's, I just wanted to show you that's kind of Boyle's law. So pressure and volume are inversely proportional. As one goes up, the other one goes down. Now, we can graph pressure and volume, and the graph would look like this. Shouldn't have those, it should be a very smooth curve, so just ignore those little bumps in it right there. That's a very smooth curve. Okay, so basically, this is a demonstration of this relationship, is that if you were to graph pressure and volume, as volume increases, look what happens, pressure reduces. And as volume decreases, pressure increases. Okay, well, what we can do is we can say, well then, if you take the pressure and you multiply it by the volume, you will always get a constant value for a given system. In other words, where the moles are constant and the temperature is constant, in other words, those two don't change, for any given system, if you multiply a pressure times a volume, you'll get a constant. And so that allowed us the development of this formula. And basically this formula says that if you multiply the pressure and the volume at any given time, it'll equal the pressure and the volume at another given time. So as long as you know three things, you can calculate the fourth thing. And that's how you'll see that we use these. I'll do an example for you in a minute. I just wanted to show you this example of an example of what the data might look like. Look at this, that as you double the volume of a container, you half the pressure. And if you were to double it again, you would half the pressure again. So this is showing you the relationship between volume and pressure for an ideal gas. Okay, but here it is. This is the relationship. This is the gas law that you're going to use quantitatively. Is as long as the number of moles and the temperature remain constant, this is the relationship between pressure and volume. All right, well, let's try an example of this. So it says the sample of gas has a volume of 150 milliliters when its pressure is 0.947 atm. What will the volume of the gas be at a pressure of this? So you've changed the pressure and the temperature has remained constant. So here we go. Let's start our question. Given. So I've been given a volume of 150 milliliters and a pressure of 0.947 atmospheres. And notice that those two go together. It says this oxygen gas has a volume of this when its pressure is this. So I'm going to call those V1 and P1. Okay, but I'm also given, it says what will the volume be? So my required is going to be my V2 is going to be my question mark. What will the volume of the gas be if the pressure is now changed to this? So I've got a new pressure. P2 is 0.987 atm. Now, with these gas laws, as long as the units are constant, you don't have to change anything. Like I don't have to change it to liters, but my answer will be in milliliters. As long as these are both atmospheres, and if this is in milliliters, my answer will be in milliliters. So I don't need to change any units. So here we go. Analysis. What is the relationship between pressure and volume? Well, P1 V1 is equal to P2 V2. That's the relationship. Basically, as one goes up, the other one goes down. And so my prediction is, notice that the pressure has increased. I am going to predict that the volume will go down. It should be less than 150. Okay, so let's sub and solve. Here we go. So 0.947, I'm subbing that in for my P1, times 150 is equal to 0.987 times V2. And now to solve this, you divide both sides by 0.987. So that'll isolate your V2. And here we go, I'll type that in. So V2 is going to be equal to 0.947 times 150 divided by 0.987, and I get 144 milliliters. Okay, so my prediction held that as I increased the pressure, I didn't increase it by much, and my volume didn't fall by much. But there is the relationship. As you increase the pressure, you decrease the volume. So again, you guys, this is called Boyle's Law, and it's showing this relationship that an increase in pressure results in a decrease in volume as long as you hold the temperature and the number of moles constant. Okay, well, let's go on to the second one. Now, before we can get to the second gas law, I've got to talk a little bit about temperature for a minute, okay? Because the second gas law is going to involve temperature, okay? So I need to talk a little bit about temperature. And basically, the first question I have for you is that is 20 kilograms twice as heavy as 10 kilograms? Now, a lot of you may think about that for a minute and go, well, of course it is. And you're right, it is. The answer is yes. 20 kilograms is twice as heavy as 10 kilograms. But now I want to ask you that same question for temperature. Is 20 degrees Celsius twice as hot as 10 degrees Celsius? And I think a lot of you hopefully will hesitate on that one. And let me help you a little bit by saying this. If you were to convert those both to Fahrenheit, and I know that's not a temperature we use that much, but listen to this. In Fahrenheit, 20 degrees Celsius is 68 Fahrenheit, and 10 degrees Celsius is 50 Fahrenheit. So I think you're kind of going, well, wait a second. You know, I've doubled the degrees Celsius there, but I haven't doubled the Fahrenheit. And so I'm going to answer this question for you, and I'm going to say no, it's not. So is 20 degrees Celsius twice as hot as 10 degrees? It's not. And the reason is that we need a scale that has 0 as its absolute minimum. And obviously with the Fahrenheit scale and the Celsius scale, you can have negative numbers. But in a minute, we're going to start investigating what is the impact of doubling temperature. Well, in order to do that, we need a scale that's a temperature scale that starts at 0. We can't have negative numbers. So we need a scale like mass, like where this, because you can't have a negative mass. Well, we need a scale that can't have negative temperature. And this was established by somebody, a famous scientist named Lord Kelvin. And Lord Kelvin established what we've now called, he didn't call it this, but we've now named it after him. It's called the Kelvin scale. And basically, Lord Kelvin helped us by trying to estimate what absolute 0 would be. And he had an interesting way of doing this. What he determined was he extrapolated backwards from 0 degrees. And what he found was that for every 1 degree Celsius reduction in temperature, it reduced the volume of the gas by 1 over 273.15. Now that's a pretty small decrease in the volume, but he used this to make a beautiful reasoning. And what he reasoned is that if every degree drop reduces the volume by that much, he said, well, if you therefore decrease it by 273.15, you technically would get down to 0 volume. And so he then came up with this beautiful kind of hypothesis was 0 degrees, absolute zero, must be minus 273.15 degrees Celsius. And from all of our measurements, he was very accurate. And so basically, we've established a new scale, and it's called the Kelvin scale, where you cannot go any lower than 0 Kelvin. And because we use degrees Celsius so much, you have to convert to Kelvin in order to use the gas laws. And so here it is. To convert, you simply add 273.15 to your Celsius measurement. So here's a good example of that. 25 degrees Celsius is equal to, well, you'd add 273.15 to 25, and you get 298.15 Kelvin. So in order to do these questions, you do have to convert all degrees Celsius into Kelvin. Okay, so we needed a scale that had 0 as its absolute value, and we developed that. That's what we need to do for these gas laws. Okay, so the second gas law is going to compare temperature in Kelvin to volume. So Boyle's law was comparing pressure and volume. Charles's law is going to compare temperature and volume. And what Charles found was that at a constant pressure, a gas's volume is directly proportional to the absolute temperature. They're directly proportional. So it's a little bit different than Boyle's law. In fact, it's a lot different. Boyle's law, they were inversely proportional. With temperature, they're directly proportional. So look at this. Volume is directly proportional to temperature. If you double the volume, you double the temperature. If you half the volume, you half the temperature. They're directly proportional to one another. Okay? And the way that works, as long as you keep the number of moles and the pressure constant, it means that for a container, the volume divided by the temperature will be a constant value. So graphically, this is what that looks like. It's a beautiful linear relationship. And this is the equation then. So for a given amount of gas at a constant pressure, V1 over T1 is equal to V2 over T2. This is Charles's law. Okay, so this is the second law, the gas law. So look at this. This is an interesting one. As I doubled the temperature here from 150 to 300, I doubled the volume. You know, as one goes up, the other one goes up. Okay, and let's take a look at our applet here. So this is interesting. I want to keep my pressure constant. I'm going to keep my pressure constant, but I am going to change the volume. Okay, so watch this. Here, let me do it this way. So watch this. I'd like you to keep your eye on the temperature. So watch this. We're saying that volume and temperature will both go up. So here we go. I'm going to, as I increase the volume, keep your eye on the temperature, I increase, the temperature increases. And as I decrease the volume, the temperature decreases. Okay? So they both go up at the same rate. Okay, so that's my second gas law. So here we go. Let's try a problem. It says a sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius if the pressure remains constant? So here we go. Let's start our question. Given. So it occupies a volume. So V1 is equal to 752 milliliters. T1 is equal to 25 degrees Celsius. and then it says what volume, so my V2 is my question mark, will the gas occupy if the temperature changes to 50 degrees Celsius? Okay, well, the relationship between volume and temperature is Charles's law. V1 over T1 is equal to V2 over T2. Okay, but before I can sub and solve, I've got to change my temperatures to Kelvin. Okay, so I add 273.15 to both of these, because that I have to use a temperature that has a 0 as its absolute minimum. So 273.15 plus 25, and I get 298.15 Kelvin. And here, 273.15 plus 50, and I get 323.15 Kelvin. Okay, so now we're ready to sub and solve. So my V1 was 752 divided by T1, which was 298.15. My V2 is unknown, and my T2 was 323.15. So I'm going to cross multiply the 323 up. So V2 is 323.15 times 752 divided by 298.15. Okay, 323 divided by, and then divided by 298.15, and I get 815 milliliters. Okay, and obviously I've increased the temperature, I'll have to increase the volume. Okay, in order for the pressure to remain constant. Remember, that's the key thing here, is that if the pressure is going to remain constant, I'm going to have to increase the volume. Okay, so that was the second law. The last law is named for another scientist named Gay-Lussac. And basically this law says at constant pressure, a gas's volume is directly proportional to the temperature. Okay, so this is going to relate pressure and temperature. All right, so in this particular case, we have basically what it says is that pressure is directly proportional to temperature. Okay, so it's the same thing as volume and temperature. And so essentially what this says is that the pressure divided by the temperature is going to be constant as long as the volume and the number of moles remain constant. And so we write that as a gas law by saying P1 over T1 must equal P2 over T2. In other words, for a given number of moles in volume, this relationship will hold. And sure enough, graphically, it looks like this. If you double the temperature, you'll double the pressure. Or if you half the temperature, you half the pressure. And sure enough, here's the relationship. Doubling the temperature doubles the pressure. Okay, let's take a look at this. All right, so here I'm just going to reset it. Let's put some gas molecules in here. Okay, and so we're interested in holding volume constant. And so what I'm going to do is I'd like you to keep an eye on the pressure. So the pressure looks like it's settling in. We'll let it settle down a little bit here. It's settling in around 12. But if I increase the temperature, look what happens to the pressure. Pressure starts increasing. Okay? So if you increase, as you increase the temperature, you increase the pressure. Okay, that's all that this law is telling us. Okay, so let's try a question here. Given A gas in an aerosol can is at a pressure of 3 atmospheres. So P1 is equal to 3 atm, 3 atmospheres of pressure, and a temperature of 25. T1 is 25 degrees Celsius. Directions on the can warn the user not to keep the can in a place where the temperature exceeds 52. What would the pressure in the can be at 52? So we'll say P2. Oops, sorry, that's not a pressure, that's a temperature. Fix that up. T2 is equal to 52 degrees Celsius. So required, what is P2? Okay, well, I know Gay-Lussac's law is P1 over T1 is equal to P2 over T2. So I'm ready to sub and solve, but before I do, I've got to convert these both to Kelvin. We can't use degrees Celsius, so I'll remember that one from the last one. I add 273, I get 298.15 Kelvin. And here, if I take 52 and I add 273.15, I get 325.15 Kelvin. Okay, so here we go. Let's sub and solve. P1 is 3 atmospheres divided by 298.15 is equal to P2 over 325.15. And so I'll cross multiply that up, and I get 3 times 325.15 divided by 298.15. Here we go, 325.15 times 3 divided by 298.15, and I get a pressure of 3.27 atmospheres. Remember that your unit has to be the same on both sides, and so that's where I get 3.27 atmospheres of pressure. Okay? All right. I said that was the last law, but there actually is one more law where you combine all these into what we call the combined gas law. So at this point, we know Boyle's law says this, that pressure and volume are going to be constant as long as the temperature remains constant. We also know Charles's law, which says that volume over temperature is constant as long as pressure remains constant. And we know this Gay-Lussac's law is that the pressure over the temperature is constant for a given volume. Well, you can actually put these 3 laws together and say that as long as the number of moles is constant, the pressure times the volume divided by the temperature is going to be a constant value. So we can, so because it's going to be a constant value, we can then compare two scenarios for a given quantity of gas, which says P1 V1 over T1 is equal to P2 V2 over T2. And this combines the 3 gas laws into one law called the combined gas law. Okay, let's try an example of that one. Okay, so it says a helium-filled balloon has a volume of 50 liters, so V1 is equal to 50 liters at 25 degrees. T1 is equal to 25 degrees Celsius and 1.08 atmospheres, so P1 is 1.08 atm of pressure. It says what volume, so I'm going to come down here and write required. My V2 is going to be my required. Will it have if the new pressure is 0.855 atm and a new temperature, the T2, is 10 degrees Celsius. Okay, So what will be the resulting volume? Well, I know that the combined gas law says P1 V1 over T1 is equal to P2 V2 over T2. But before I can do it, I've got to convert. I know that 25 degrees, I add it to 273 and I get that's 298.15 Kelvin. Remember, you've got to convert temperatures to Kelvin. And here, this would be 283.15 Kelvin. Okay, we're good to sub and solve. So P1 is 1.08. V1 is 50 liters divided by T1, which was 298.15 Kelvin, is equal to 0.855 atmospheres times V2, which is our unknown. I'll just leave it as V2. And then divided by 283.15 Kelvin. Okay, so my units are the same on both sides. So what I'm going to do to isolate V2 is I'm going to multiply the 283 up to the numerator, and I'm going to divide, so the 0.855 comes down to the denominator. So V2 is going to be equal to 1.08 times 50 times 283.15 divided by 298.15 times 0.855. And here we go. My final answer is 1.08 times 50 times 283.15 divided by bracket 298.15 times 0.855, and I get a volume of approximately 60 liters. Okay, so that's showing the application of the combined gas laws, combining, a bunch of these changes within a a given amount of gas. So I haven't changed the number of moles. Okay, so I've got some questions here for you to try. I would like you to try this one, page 435, number 4, page 451, number 2, and 461, number 1. It's just some applications of those, and there's the answers given right there. Good luck, and let me know if you have any questions about the gas laws.